In the last couple of videos, we have been talking about the electronic configuration of multi-electronic atoms. We have introduced a variety of concepts, including the electronic spin, the Pauli exclusion principle, and then the concepts of shielding and penetration, to determine that for the first few atoms in the periodic table, the electronic configurations are like this. For lithium, it's going to be 1s2, 2s1, and so forth, right? So what we do in this video is wrap up the discussion of the periodic table by saying just a few more details that we need before we can actually get write the entire electronic configuration for the entire periodic table. Some of the things that actually are necessary for this is to again remember that while in hydrogenic atoms, the energies, the 2s and the 2p orbitals are actually the same. Okay, so you would write the 2p orbitals at the same energy level. For multi-electronic atoms, okay, because you have shielding, which affects differently to 2s and then to 2p orbitals, you actually have that those electronic energies are different. And again, that means that this will be the electronic configuration for the hydrogen atom, helium, there will be lithium, this will be beryllium, and then there will be boron. Okay. Now, a question is, well, how do the what is the orbital ordering beyond the 2p? And when this can get a little complicated, there's actually a very easy way to write it, which is to simply do this. You just write all of the possible wave functions in the hydrogen atom in this tabular form, and then there's a way to actually predict what the orbital ordering will be using a simple trick. Okay, 5p, 5d, 5f, 5g, and again you can continue to write this all the way until infinity. Okay, which we're not going to do. But in order to predict what the energy ordering of the orbitals will be, you simply have to do this. Okay, the first orbital will be the 1s, the second wave function 2s, and then 3p, 2p, 3s, and 3p, 4s, and so forth. Okay, so that tells you what the ordering of those orbitals will be. Okay, which we can write as follows: 1s has lower energy than the 2s, lower energy than the 2p, lower energy than the 3p. 3s, the next will have 3p. Then you will have 3p, 4s, and then after 4s you have 3d. Okay, 4s, 3d, and then after 3d, 4p, 5s, and so forth. Okay, so again, that describes all of the possible orbitals that you can have for atoms in the periodic table. Okay, so that takes care of the problem of the orbital ordering beyond atoms of lithium and boron and so forth. Now, that is the electronic configuration for boron, which has 5 electrons, and then we come to carbon, which has 6 electrons. So we actually know that the electronic configuration for carbon is going to be 1s2, 2s2, 2p2. But here we actually have a choice, right? Notice that that 6th electron, if this is the electronic configuration for boron, that 6 electron can have wave functions that can be slightly different. For example, we can say that that maybe that 6th electron has this wave function. Okay, so it will be a 2p wave function with antipedal spin. Okay, then the same if this is the 2px, right? So that would be the same orbital. That's one of the possibilities. Another possibility would be this. Okay, which means parallel spins. Okay, but different 2p orbitals, or the ML changes. And yet another configuration would be this. Okay, so the electrons are different, in orbitals are different m sub l, but the spins are anti-parallel. Okay, you can have exactly the same last 2 choices with this orbital. It would not change anything. This is exactly the same as having the electron there, and this is exactly the same thing as having that electron there. Okay, so the question is, which one is of lowest energy? Well, it turns out that the situation that is of lowest energy is the electron being a different orbital, not in the same, but different, either that or that. Okay, and then the spin is parallel. Okay, now that the electron is in a different orbital, or on an orbital of different m sub l, okay, 2px and 2py, that can be simply explained from the fact that, well, electrons are negatively charged particles, right? And if they're in the same orbital, 2px, okay, they're going to be repelling each other much more so than if they're in perpendicular orbitals, right? 2px and 2py. The electronic repulsion is going to go down if they occupy different orbitals. That is simply explained with electrostatic considerations. What is not so easy to explain is the fact that the spin of the electrons should be parallel. Okay, so again, you have electrons in two perpendicular orbitals, here and then there. Okay, and it turns out that it matters, okay, if the spin of this electron is up, then it turns out that it's of lower energy to have the spin of the electron also up. Okay, that is of lower energy than having them antiparallel, even if they're in different orbitals. There's no easy way to explain this. This is actually a purely quantum mechanical effect, and we have an analog in the macroscopic world that allows us to understand that, but we actually know this from experiment. Okay, so that's what we call the Hund rule, or Hund's rule. And again, it says that when you have a choice, okay, you always like to place electrons in different orbitals and with parallel spins. Okay, so with this we can actually continue on and then try to figure out what the electronic configuration for the rest of the atoms in the periodic table would be. For nitrogen, that will be the electronic configuration. Okay, the next atom in the periodic table will be oxygen. You will have that. Then you will have fluorine, neon, and then you can start to fill the rest of the orbitals, 3s, 3p, and so forth. Okay, so this is what we call the Aufbau principle, which generally is studied in general chemistry. Okay, but what we have here is try to flesh out a little bit those ideas from wave functions and the solutions of the Schrödinger equation. But again, you can see that from now on, you can continue down the periodic table. There are exceptions to these rules that we have introduced here, but for the purpose of this course, they're not going to be that important for us.